Good afternoon, Chemistry 1 honor students from Destrehan High School. Today is Thursday, April 23rd. Today we are going to be talking about resonance structures um, and what they mean. Um, as far as formal charges, I'm not going to go into that because you don't need to know that. That's a Chem 2 concept. Um, what I'll kind of tell you what it means, but I'm not going to go into calculating it or anything like that because it's just extra information that you're not going to need to know. You're just going to need to be able to identify that there are alternate structures, which is what resonance is. Excuse me. All right. So in order to do this, you need to recall that there are some steps to drawing Lewis structures. Um, So basically 4 steps that you need to know to be able to draw a Lewis structure is first you need to be able to determine the total number of valence electrons. That's for all of the elements or atoms that are involved. You write a skeletal structure of the molecule. You use the two valence electrons to form each bond in the skeleton structure. Then you try to satisfy the octets of the atoms by distributing the remaining electrons. So going through, um, and let's kind of look at this. I'm going to cover these up just so that I can talk about it in stepwise. All right. So going through, if I asked you to write a resonance structure for the nitrate ion. Nitrate, remember, is NO3 with a -1 charge. And that's why it is an ion, because it has a charge. All right. So looking at these, go through steps 1 through 4. So the first thing that we have to do is determine the available electrons. So nitrogen has 5 electrons. There's only 1 nitrogen, so 1 times 5 is 5. There are 3 oxygens. Each oxygen has 6. And then this one comes from that -1 charge that we've added 1 extra electron to that. So it gives us a total of 24 electrons that we need. All right, so we're going to draw our skeleton structure, NO3. All right, now we're going to draw a single bond to each of those. And that is using 2, 4, 6 electrons. And then we're going to fill the octets of each of the oxygens. All right, so now we've used 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons. All right, so that is one version of it, but what is the problem that we have right here? When we look at nitrogen, nitrogen only has 6 electrons around it. So what that means is that one of these pairs of electrons needs to go away, and we need to make a double bond. Let me erase that. And so one of these is going to be a double bond. Now, when it comes to resonance, we have to figure out how it's if there's a best way to draw that. All right, so let me kind of move some things out the way. So this was just going through, and I just didn't want y'all to see it while I was doing it. But if we just follow the rules, we end up with this. And, so why is this structure better than this one? All right, well, the reason why is because in this structure, nitrogen does not have an octet. So we have to have an octet. So we moved one of those pairs to form a double bond. Now, so what resonance means And let me go back and see. What resonance basically means is that there is more than one possibility for the structure. So drawing this like this, all right, so we have this, this is the structure we just drew, all right. It's going to be NO3, and then we put brackets around it and show that it's got a -1 charge. All right, that's just because the compound that we're using is NO3 negative. If it was one that didn't have a charge, you wouldn't have to use the brackets or anything like that. So you can do resonance structures with compounds that don't have a bracket. All right, now, so this is one possibility for drawing the structure. Now, this is going to seem kind of redundant or seem kind of obvious, but the thing that we can do with this is this double bond doesn't have to be in this position. The double bond can be at any of these three areas, three bonding sites. So a second alternative for this one would be if we shift the double bond from here to here. Now, when we do that, we have to maintain an octet around the oxygens. So this oxygen has a single bond, so it has 2, 4, 6, 8 electrons. This one has a double bond, so it has 2, 4, 6, 8 electrons around it. Now, that still, everything has double bonds. And when you're showing a resonance structure, typically you're going to show an arrow that it can go back and forth. All right. Now, there's still a third possibility because we can shift the double bond from there to there. All right. So when we look at that, we can see that the third possibility is the double bond has now moved to right here. And again, we shifted the electrons to show that we have an octet around this oxygen, an octet around this one, and an octet around there. And then it also gives us an octet around nitrogen with 2, 4, 6, 8. Now, there is something called formal charge. What formal charge does is tells us which one is the best. What I can tell you on this one is that all the structures on this one are equivalent. All right, meaning that these structures these shapes would be seen equal amounts of time in nature. All right, all that's really happening with this is the molecule is flipping. So we turn the molecule to where this oxygen is now up, and then we turn it again where it's down. That double bond is going to kind of appear at different places at different time, essentially 33.3% of the time. All right, it's not permanently in that location. All right, now I'm going to put it all together. I included this worksheet in the assignment today for you to print out, or you can just kind of look at the elements that we're doing and kind of do this together. So that I want to put all of the steps of this together. So one of the things that we're going to do is we're going to draw the Lewis structure. We're going to determine the shape of it, both for electronic geometry. So I'm going to call that EG, electronic geometry, and molecular geometry. And then we're going to talk about polarity as well with this. All right. All right. So we're going to talk about polarity as well. All right. So let's look at PBr3. So one of the things going way back, we could identify the name of this, and that's going to be phosphorus tribromide. Don't really need to know that, but I just wanted you to kind of remember that. The tri comes from the 3 right there because there's 3 bromines. and phosphorus is P, Br is that. All right, so I'm going to go ahead and erase the name because I want to make sure I have enough space for everything here as we go through this. All right, so go back, look at your notes for the steps for drawing the Lewis structures. There's different ways you can do it. You can do just the available electrons, draw the skeleton, or I like to use the needed, available, shared method. All right, and so the reason why is because it helps with getting the right number of bonds and things like that. So phosphorus is in column or group 5A. So phosphorus is going to have 5 electrons around it. Each bromine is going to have 7, and there's 3 bromines, so that means there's 21. So as far as available electrons, that's going to be 5 plus 21 is 26 electrons available. All right. Now needed, each of these atoms can get a full octet with 8. So we're really just looking at 8 times 4 for our needed, which is going to be 32. So in order for everything to be full, there's 32 electrons. Remember, this number, the needed, doesn't mean anything to us. It just helps us determine the number of electrons that we're going to share. So 32 minus 26 is 6 shared electrons. All right. And so since they share in pairs, if we divide that by 2, that means that there are 3 bonds. All right. The reason why I do that is I want to be able to know if I need a double bond ahead of time. And you're going to see how that works in a minute. All right, when we do the next one. All right, so let's draw the Lewis structure. I'm going to put my phosphorus right here. And then I'm going to spread my bromines out equal distance around the phosphorus. All right, really doesn't matter where you put them. I'm just spreading them out and going from there. Now, each of my bromines, I'm going to give electrons to give it a full octet. All right, so each of my bromines have a full octet now. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. But how many electrons do I need? Or how many electrons do I have available? I have 26. Well, if I've used 24, that means I have 2 electrons left over. So where do I put those 2 extra electrons? We have to put the 2 extra, and notice what's wrong with phosphorus here. Phosphorus only has 6 electrons around it. So if I put 2 more to finish out that octet, now phosphorus has 8. Each bromine has 8. All right? So that is the Lewis structure. Now, what about the shape? So electronic geometry, e.g., how many areas of electrons do we have around phosphorus? We have 1, 2, 3, 4 because we have that lone pair. Lone pair counts as a place and each bond counts as a place. So we have 4. So I'm coming right here and it's not going to let me draw, but I'm coming here to this section where I have 4 and 4. All right. So all of these sections of 4. Now, the next thing I need to look at is how many of those are bonded. So I have 1, 2, 3 that are bonded. So that means that I'm at 4, 3. So for there, I can look that has one lone pair right there, and it's tetrahedral. All right. So my electronic geometry is tetrahedral. All right. My molecular geometry. So looking at this, my molecular geometry, based off of that, 4, 3, and 1, is going to be trigonal. Pyramidal. All right. Now, the next question we want to know is, will this will this atom be a polar or non-polar atom? Well, for this shape, it's actually easy. See these lone pairs right here? That is actually going to make this atom polar, polar because it's going to push like that. So when we look at it over here, when we look at this over here, we would have those 2 electrons right there, and that's going to make it a polar one, and so on from there. All right, I'm going to do a couple of others with you, because this one was easy because it was really only one shape that was involved. Here's the problem with this one. So we need to look at N2H2. There's 2 nitrogens and 2 hydrogens. So that means we're going to have 2 central elements. So it's not going to follow this one per se. We could actually have 2 different structures in this one. And I'm going to show you what it means. All right. So doing my needed, available, and shared, just so that I can get everything. And oddly enough, the needed, available, shared is going to give us the right number of bonds and everything. All right. So we need 12 electrons total, because each nitrogen has 5. So 5 plus 5 is 10. Each hydrogen has 1. So 10 plus 2 is 12. Available, each nitrogen needs 8 to be full. So that's 16. Each hydrogen needs 2 to be full. So that's 4. So 16 plus 4 gives us 20. And so that means we have 8 electrons that are going to be shared. All right, if we divide that by 2 to get our number of bonds, it means we have 4 bonds. Now, how do I know which one to put in the middle? Well, I know that each hydrogen can only make 1 bond. So that means the hydrogens have to be on the outside, and nitrogens can make up to 3 bonds each. Actually, you can make up to 4 bonds each, just depending on how it does. All right, so I have a hydrogen over here. Let me draw that right. Come on, there it goes. All right, so I have a hydrogen on this side, and I have a hydrogen on this side. All right, that gives me 2 of the bonds. Well, I need 4 bonds. So what that tells me is I'm going to have a double bond right here between these 2 nitrogens. And so what does that do? That gives 6 electrons around this nitrogen, 6 electrons around this nitrogen, 2 around this hydrogen, and 2 around this first hydrogen. So hydrogen is satisfied. All right, but we've used 2, 4, 6, 8 electrons. We have 12, so 10, 12. How do I know they go on the separate ones? Because this one had 6, so that gives it 8. This one has 6, so that gives it 8. Now, if we look at the VSEPR table, or VSEPR table, all right, we have some different things going on here. So what I want to do is I want to just look at part of this compound. I'm just going to look at this nitrogen and this hydrogen. So I'm just going to look at one side of it, and without that extra hydrogen on there. So I know that there's a bond there, but I'm going to pretend I don't see that for right now. So just looking at this structure right now, I want to look at this nitrogen. So I have 1, 2, 3, 4 areas. So I have 4 areas, and then I have 2 sides that are bonded. This double bond counts as one bonded side. So 1, 2. So I'm going to 4, 2. And then as far as lone pairs are concerned, that doesn't apply on this one. But the shape that we get is tetrahedral bent. So what really is going to happen here is, looking at this, we need to actually draw a bent structure. So you don't have to erase it on yours. I just wanted to kind of show you from the chart what's going to actually happen. So because this nitrogen has an electron pair on it, it's going to push that hydrogen down a little bit. Now the same thing would happen on the other side. And this hydrogen will get pushed down. So this structure is actually a bent structure. Now, again, if we look at it, we have these lone pair electrons on this side. We have these hydrogens that are sharing their electrons with nitrogen on that side. So what that's going to produce is a more positive side here and a more negative side on the nitrogens. So this one would be polar as well. All right. Looking at this, go ahead, skip number 3. Try number 4 on your own. And I want you to skip number 5. And then you should have had some more. We can do this one. We can do this one. I want you to skip 8 because it's a little bit beyond what we need to do. Skip 9 and do 10. All right. So I'm going to do 10 with you right now. And then we will, and then if you want to pause the video and try to do the rest of them, I'll show the answers for it or show the shape for it. So looking at 10, notice that there are 6 fluorines here. This is one of the exceptions to the rule. This is going to have what's called an expanded octet. All right. So elements that occur on period 3 and down 3 through 7 have an available d orbital that you can fill that may not necessarily be full already. So if you notice that sulfur is on period 3 and it doesn't have anything in its d orbital. So we can actually shove some electrons in its d orbital on this one, and that's why we can make this expanded shape. So on this one, I'm not going to do needed, available, shared. All I'm going to do is look for my available electrons. So sulfur has 6 electrons available, and each fluorine has 7. So that gives us a total of 48 electrons, because 6 plus 7 times 6 equals 48. All right. Now, drawing this one, sulfur is the element by itself. Now, I need to put 6 fluorines around it. So I'm going to kind of, let's draw it a little bit better. All right. There's kind of a trick to be able to draw these. If you put 1 fluorine on top, 1 fluorine on bottom, and then you put the fluorines as an X on the sides, it kind of automatically equal distances them apart, and so each one's going to have a single bond. It would be kind of weird to have a funky double bond thrown in there and all of that. Now, going to go ahead, put our available electrons around the fluorines to fill the octets. So, looking at this one, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. There's our total number of electrons. All right. Now, going through this, this is what the structure would look like. Now, if I want to know what the shape is, I need to find one that has 6 electronic domains, 6 bonded areas, and then and no lone pairs, because we didn't have any lone pairs on there. So the shape of this one is octahedral. Because it has something bonded on 6 sides. So that is our electronic geometry. Our molecular geometry, again, would be octahedral. All right. So this one happens to be octahedral. And the reason why I wanted to point this one out is talking about polarity. All right. So I'm going to actually show you on this drawing. Do you see how nice and symmetrical this drawing looks? And same thing with this one, how it's the same thing all the way around it. So that's going to make this one non-polar. All right. So in general, symmetry, if it has the same thing all the way around it, or if it's a balanced structure, it's going to be non-polar. If the shape is unbalanced, like we had, PBr3 here, where we have these lone pairs here, it kind of makes it into a polar molecule. Same thing with this one, except for it had 2 central molecules. This one is polar as well. So what we have to kind of look at is what about the shape makes it polar or non-polar. All right. So I'm going to actually help you out on this. Let me grab this so that I can expand this out completely. All right. So I'm going to kind of show you on this sheet right here some things that make you do that. In fact, hold on just a minute. All right. So when we're talking about polarity of this, if we look at this sheet, and you can write on your sheet if you printed it out, some things that this can look at. A linear molecule is going to be always going to be non-polar. All right. So when we look at this, linear molecules will always be non-polar. They will always they'll always kind of have that shape. And that's one that has 2 electron domains, 2 bonded domains, no lone pairs. Notice this one is 3, 3, and no lone pairs. This one is always non-polar, this shape. Trigonal planar. All right. So we have 3 electron domains, 2 bonded domains, and 1 lone pair. So we actually have these little electrons right there, and that's going to make this have a dipole moment that's kind of shaped like that, and that it's going to become more polar. All right, tetrahedral, tetrahedral, no lone pairs. So this one is non-polar. All right. So going through here, has 1 lone pair on this one. So 4, 3, and a lone pair. So we put that lone pair on there, and then now we get this dipole that goes like that, makes this one polar. All right, tetrahedral bent, 2 lone pairs. This is actually what the water molecule looks like. we're going to have 2 sets of oxygen, 2 sets of electrons there, making this one polar in this direction. Now again, this little arrow that I'm drawing, the head of the arrow is always means that there is a partial negative. The tail over here where it has the cross on it tells us that there is a partial positive. All right, and that little sign that I'm drawing is a lowercase sigma. It just means partial in chemistry. All right, getting back to this one. There are no lone pairs, so that one makes this one non-polar. Now, there is a situation where this one could be polar. Let's say that we had something like, and I'm just going to make up a bond here, but let's say we had something like sulfur, where it's bonded in 5 places to chlorine, 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 and then one of these is a fluorine. All right, this element being different throws off the balance. So when you have that one different element in there, now it becomes polar. All right, if it's all the same element around it, it's perfectly balanced. See how these are equally distanced apart, these are equally distanced apart, so it makes it nonpolar. But when these, it's still equally distanced apart and is still balanced, but that fluorine is different, so it makes it a polar molecule then. All right. So this one is always going to be polar. All right. This one has 2 lone pairs, so this one's going to be polar. Now, so on this one, at this point, you might be thinking, well, if it has a lone pairs, it automatically makes it polar. But notice what happens on this one. It's a linear molecule. The electrons, and it's hard for me to draw this, but the electrons are spread out around it equally. All right? So when this happens, this one is a non-polar because it is balanced. It's symmetrical. And then going through, this one is non-polar, but if one of the elements is different, it could possibly be polar, but that's only if one of those elements is different. All right, on this one, the lone pair would be down here. This one is polar, and then this one, we have 2 lone pairs, 1, 2, 3, 4. Notice that they are balanced and symmetrical, so that makes this non-polar. Let me make sure I don't have any other. That's it. That's all the shapes I have. Now, on our test, we're not going to go past any of them that are 4. I wanted to teach you the other ones so that you know and you've seen them in the future should you choose to take AP Chemistry or Chem 2, something like that. You know what they are and you can see them. All right, so just kind of be aware of that, and be cognizant that these other ones exist. I would, if you plan on taking the next level of chemistry, I would hang on to this sheet and just have it available and all of that. All right, so thank you for listening today. At the end of this, we should be able to complete all of Chem 101 homework 10. Email me if you have any questions. Tomorrow I will open up the assessment. The assessment is going to be Unit 9 and 10. I may do a real quick video review that just kind of summarizes all the topics and all the outcomes that are going to be covered on this test, on this quiz. I still haven't fully decided if I'm going to give you a constructed response portion or not, but I would be expecting about 20 questions total. And part of the submission may require you to email me or submit your work to me. Probably the easiest way to going to be able to do that is take a picture of it to me and submit it to me online. If I do that, I'll have you submit it through Google Classroom or something like that. Or you could do it as a in Google. Let me pull this up. So if you're in Google, in your thing, if you go to Docs, there should be one that is Google Draw. You might have to search it. So, yay, they gave us this little funky thing now. Yeah, Google Drawings. So if you want to do it, if I have you draw some of the molecules or something like that, you could use this to draw it. If you know another way that you could do it, you can do it that way as well. I'm not super familiar with this program and how it works, so that's really up to you on how you want to approach it. Y'all don't need to see that. I have to clip that part of the lesson. All right, so just kind of be aware that that's going on, and that you can use those. All right. So if you have questions or comments, email me, and I will get back with you as soon as I can.